So now we are going to talk about electronic mail security. Now here's the thing. Most of these chapters that we're going to talk about from now on are just going to use the same thing that we have learned. This is application of the same ideas. So we know how to authenticate people, we know how to authenticate messages, we know how to encrypt things. So all of this is basically a catalog of what somebody selected from what we have learned. There is no new encryption algorithm or new anything here, basically just a catalog. Okay, we are going to allow AES, we are going to allow this, we are going to allow this, and that's this scheme. Other scheme allows this, this, this. So it's mostly a catalog of the techniques that we have already learned. So we're going to talk about three different mail efforts. One is called PGP, second is S-MIME, and third is DKIM. What we need is confidentiality, for which all we need to do is select a set of encryption schemes. Authentication, for which we need to select a set of hash schemes. Integrity, similarly like hash. And non-repudiation of origin, basically we have to select again something like source authentication, right? So that's what we will do. PGP. So the very first one that was done is, and very popular, is PGP. And this is from pre-Outlook days, when there was no other secure way to do anything. And this is interesting thing about this effort is that this is done by one person, Phil Zimmerman. He spent his life doing this. Obviously he is a millionaire now, I suppose, but he started out as just for the good of the society. So what he did was, he is a cryptographer himself, so he selected the best techniques and put it into a single package that anybody can use, and that runs on any system anywhere in the world. And guess what? He got caught by the State Department for export violation. He was tried. Can you guess what the public response was? Everybody spoke in favor of him. This whole 40-bit versus 128-bit we talked about, right? You cannot export anything 40-bit. You cannot export any confidential information like this, that. So how what he did? He published a book from MIT Press. MIT Press published a book which was nothing but the source code. You can OCR that book, and it was written in a font that is best OCRable font, right? So the problem of the day was that the government said you cannot export the source code. You cannot put the source code on a website that anybody in the world can do when it is such a sensitive matter. It's like putting how to make nuclear reactors on a website, right? You cannot write encryption algorithms, and things like that on a website. Source code. So he published the book. The book is exportable, because the copyright laws do not have any export restriction, but the code is not. And MIT Press obviously was with him, and they published the book, and they said, okay, now anybody can buy anywhere in the world who wants to buy this book, and we won't send you the code. So the government then finally realized that they are really on the wrong track, and they left him alone. After that, his company, his code was bought by one company, that was bought by another company, that was bought by another company, now known as McAfee. So, basically, I'm sure in this process he made a few millions, and so he's all set. Anyway, the PGP became so popular that other people wanted to make products which were compatible with this. So they went to IETF and said, why don't we set up a standard? And so there is a standard called OpenPGP. So OpenPGP products work with each other, right? Because they use the same set of things, whatever OpenPGP says. All right, all that story, let's see what PGP decided. So for authentication, Zimmerman decided to allow SHA-1, 160-bit hash of the message. So you hash the message, then sign it with your private key, ERA. A is the source. You basically encrypt that hash with your private key, then combine, concatenate with the message and send it over. On the other side, you just do the opposite. The public key is available to anybody. Anybody can compare and say, yeah, you sent it. Encryption is straightforward. It allows it allows RSA. No, not allows RSA. Basically, it uses any secret key algorithm, but the secret key is sent by RSA. So you select, the sender can just arbitrarily select any key, 128-bit key, and encrypt the message and attach to it the key which is encrypted in the public key of B. So you need a certificate from B. As long as you have the certificate, just like Outlook, if you have my certificate, you can send me an encrypted message. If you want to do both, no big deal, just do both in a sequence. First you do the signature, then you do the encryption. So basically MAC then encrypt scheme, and then you do the opposite, decrypt and then MAC. Compression. So one more thing that it does is that it compresses the message, because most messages are text messages. They have a lot of redundancy and you don't want to spend so much time basically sending those bits. So it uses zip. The compression is done after signing, so that's important. As to what you do, first compress and then sign, or sign and compress, sign and compress. And he obviously selected first sign it, uncompressed message. So everything, all these spaces, everything is done. And then you compress it, because later on you may want to store. So signatures can be stored, and the compression algorithm may not be around. So you want to keep it in uncompressed form. So next question is, how do you send non-ASCII characters? And this is true for all mail messages, not just secured mail messages. All messages have to worry about how to send it. And PGP selected radix 64 or base 64. Everybody has a different algorithm. So for example, Outlook might have a different one and somebody else, but PGP selected base 64. And there are many such algorithms which convert any binary text into mailable text. So in this one, base 64 or radix 64, what you need is 64 characters that can be mailed, and so those are 26 A to Z uppercase, 26 A to Z lowercase, that makes 52, 10 numbers 0 through 9 makes 62, and then you have 2 more characters which are allowed. I think those are equal to and number, I forget the number, those 2 names. Anyways, there are 64 characters which are allowed to be mailed, no carriage return, no line feed, no anything else, right? So what you do is you take whatever you want to send, let's say MAN you want to send. Now these are all mailable characters, but they are not 6 bits. We want to convert everything into 6 bits. These are all 8 bits, right? So when you convert them into radix 64, you convert everything into 6 bits. The way you do it is you write down 8 bits first. If you take 3 characters, the total would be 24 bits. It doesn't matter what the characters are. They could be semicolon, they could be carriage return, whatever you want to say. So there will be 8 bits each. 8 bits each, you get 24 bits. Divide them into 6, you get 6 bits. Each of those 6 bits is translated into the code that we just talked about. So even though you want to just send MAN, you send PWFU. Now, just like base 64, radix 64, there is radix 32, there is radix 16, there is radix whatever you want, basically. So in some system, for example, the lower case may not be allowed, so you don't get only 26 uppercase in some mail system. So then you those take 26 plus take 10 numbers, that is 36, and you use, well, not all 10 numbers, you just use 32 of those combinations. So don't allow certain combinations, certain letters, maybe Z don't allow or something like that. So you just allow 32 letters, and then you divide everything into 5 bits. That would be radix 32. And using this method, you can send any binary information. You can send your photograph using this method. If you want to send a photograph, you just take the bit pattern, divide them into 6 bits, and you get the ASCII, send it over. All right, so now summarizing, you take a file, sign it, compress it, encrypt it, convert. After encryption, you do the conversion to Radix 64 just before it goes onto the wire. Right? So clearly this is a lot of binary here. Although M, A, N are no longer left here because they're encrypted, so everything is binary anyway. So then you do the conversion. Here you convert back to binary and you do the rest. So the session keys, it allows a number of session key secret algorithms. It allows 56-bit DES, 168-bit triple DES, 128-bit cast. So cast is an algorithm which was developed by Carly Adams and Stafford Travers, whatever how you will pronounce it, and has become popular. And then there is another algorithm called IDEA, International Data Encryption Algorithm. So we did not talk about those, but they exist and they're used here. And you can even use cast 128 to generate a key from the keystroke timing of the user. So if you really want a, so PGP, you're running PGP and you're sending an email. So PGP has to decide what should be the key for your email. It could just time your keys and say, well, you're typing fast, typing slow, and depending upon your typing speed, it will determine a key. Next invention is your private and public keys. So you could obviously get a certificate from RSA or from whatever company you got your certificate from. But in those days, certificates were kind of expensive in the original days, and there were not that many companies, there was not that much competition, and therefore you really had to pay heavily for getting the certificate. And so he said, okay, we don't need any company to give you a certificate, any person can give you a certificate. Oh, before we come to that public, that is next slide. On this slide, what we are saying is that you could have multiple certificates, which is possible even today. I mean, like, you don't have to have one certificate. You could go to one company, get one certificate, go to another company, get another certificate. You can get as many certificates as you want. It's like, how many driver licenses can you have? You can go to one state, get one, another state, get one. Generally, they will not give it to you, but some states might. And then, similarly, several countries will give you passport, if you have some reason for that. So you can have multiple certificates, right? So this allows that. And so every certificate, every key has an identifier, which is basically the 64-bit of the key. The key itself might be 1024-bit, but the least significant 64-bit of the keys. And signature keys are different from encryption keys. Now this is another general principle. I think I may have talked about this earlier, but I want to emphasize that this will show up in many, many applications. You do not use the same key for encrypting as you use for signing. It's like this. You don't write your letter in the same handwriting that you sign. Correct? Your signatures are a little bit more difficult to copy than your handwriting. And the reason is because if you go to the court may say, well, we want to decrypt this, give us the key. So the encryption key can be what they call, need to be disclosed, right? But once you disclose your signature key, for example, if suppose you didn't disclose signature key, then you are all free. Anytime somebody says, well, this was signed by you, say, no, somebody else made it up, I told my key in the code that day. Alright? The signature key, nobody can ask you to disclose, and you never disclose it, so that your signatures are valid for life. Encryption keys can be asked to be disclosed. And obviously you should not use the same encryption key for multiple documents. For one, second, third, everything you should use a different key. And they could be asked for disclosing each one of them. For signing, you can use different keys or you use the same key, whatever, doesn't matter, but you should not disclose those, because signature is good for life. So the message format, basically you have to put all this information into the message. First thing you have to start, what is the key that you use, the key ID. With that, you encrypt the session key. And then you have the timestamp, so that there cannot be a replay attack. Key ID again. And then leading 2 octets of message digest. Alright, this is in clear, and then the message digest. So the message digest is encrypted. This notation here, E, means encrypted. This is encrypted, but this is clear. So you get the message digest, and you take the first 2 bytes, you put that in clear. Rest of it, actually the whole thing you send it in encrypted. And this is just a double check because you have multiple keys. Maybe my key ID number and your key ID number, this just happen to match in 64-bit, but they are different keys. Right? To avoid that possibility, they put 2 bytes in clear, so you can double check that, yeah, this is the same key both of us use because the first 2 bytes are same. So because there are multiple keys and key IDs is simply 64-bit, there is a possibility of a clash. So they put 2 more bytes here in clear, okay? And then basically data and file stamp and whatnot, and that is compressed and encrypted, and you can see the keys. This is compressed, this is encrypted, and this is R64. So we talk about key rings. We already talked about it. Basically, you maintain a table of keys and of all the correspondence. Private keys encrypted by a passphrase, and the public key of all the correspondence. You keep your own keys and their keys. It's like a key ring. And with your own key, you keep the timestamp key ID, which is 64-bit, public key, private key, and your own ID, and similarly here. You keep the timestamp key ID and signatures, trust. Signatures and signature trust. So these are the 2 new fields which we have not defined. Signature trust. All right, I'm going to define in the next slide. But basically, keep tables of all the keys. And so, not next slide. Let's just next one slide will come, which will talk about the trust. But let's see. This is basically a diagrammatic representation of the previous tables. Is that you have to have a passphrase that is required to read this private key table. So if your computer gets hacked, they can get the table but not the information unless they know they have the passphrase. Right? So that's why they need a passphrase to read the private key table. Public key table anybody can read. All right? And the rest is all as before. You encrypt and sign and so on. So reception just the opposite. So there's nothing new there. All right. So then the question of trust. So I was saying that in those days certificates were expensive, and this guy is a freak, freeware freak, and he didn't want anybody to charge for anything. The Software Foundation or Free Software Foundation, whatever that is, right? FSF, Free Software Foundation. Yeah. So he said that anybody can give certificate to anybody as long as, so suppose I say that this is Jing Minzi, so because the professor said so, maybe somebody will trust more that, yeah, this is Minzi, than if a student said that this is Minzi, right? So depending upon how much we trust somebody, we can trust the certificate issued by that person, right? And if this person gets enough certificates from different people, we can elevate him or her to a higher level of trust. Because 5 people said this is Minji, right? So that way kind of guaranteed that this is, the person, right? So that's the kind of idea he brought in, is web of trust. And I remember going through this process myself, that, and not long ago actually, I remember it was in St. Louis. So St. Louis means 2005. You could look up list of people who are part of the web of trust, and you could call them and say, well, I want a certificate from you. You would go and meet them and give them your driver's license. Say, yeah, okay, all right, here's your certificate. And then you get 2 or 3 people you meet, and then you get a real, high level of trust. And then now you can start issuing the certificates. So this is how it works, is that your trust for these different people, A, B, C, D, E, F, G, H, and to S, is different. Is different for them and different for certificate issued by them. So here is the notation. This dot means key is deemed legitimate by you. So you just trust this key. Blank circle means key owner is partly trusted by you to sign the keys. So you trust the certificates that they issue, partly. All right? A gray circle means key owner is trusted by you to sign the keys. And when we say X to Y, in arrow going from X to Y means X is signed by Y, and this one is the unknown key. Okay, so like now having those notations, let's see few examples here. S has two keys, two certificates which are, we don't know them, who signed them. Alright, so I cannot trust S much. Because he has two keys, one from Russia, one from some other country, and so on and so forth, and we don't know any of them, so we just cannot trust them, right? So this is a bad example. Here is one. R has a certificate from N. You see this arrow means X, arrow from X to Y means signatory is Y, Y signing. So N is giving a certificate to R. Right, and we trust N and we trust the certificate. Let's see. They are dark and the circle. So partly trusted. So we partly trusted the certificate. We trust N fully, but we partly trust the certificates issued by him. Only partly. Whereas this P, we trust L and we trust the certificate issued by him as well. The P is kind of trusted then. So you can keep going here and let's see. There is a half gray here. When we trust partly, we have half, so there is a whole 0 through 1 number, level of trust. And so if you read all of this, the summary is D, E, F, L are trusted. D, E, F, and L. These people are trusted because we trust them to sign and we trust them totally. Okay? D, E, F, L. Those are the one with full circle, gray circle with a dot inside. A, B are half trusted. A and B are half trusted. S is untrusted because certificate that he has or she has is not trustable. So he produces whole algebra of trust. By the way, having said that, 5 years ago or 6 years ago, I was looking into this. Since then, I have not looked into it. So I think this is gone. And the primary reason is because now there are free certificates available, like all of you got the certificate without paying, so why go for this web of trust issue, at least for mail. Okay? So now this is more of history. M and A. M and A? Yes. Okay. Yeah, this is just basically why is M, okay. First of all, M is certified by E. So we trust M because we trust certificate issued by E. We trust M, but we don't trust this. We don't trust see, the thing is, clear means we don't trust the certificate issued by M. We trust M, but we don't fully trust the certificate issued by M. Here, we trust A. Now it doesn't say who gave the certificate to A. Somehow we trust A, but only half we trust for the signing the keys. So that's the difference between here. We don't trust him at all for signing the keys. We trust him half for signing the keys. Now there are two guys, G and H. They are signed by A. So we trust them half, right? But it turns out that the H is signed by two half guys. A signs it, we trust H, and B signs it. Both of them are half trusted, but since both of them signed H, we trust H fully. So there is this thing about, you get half of the trust from here, half the trust from here, and add up and you get full trust. But still we don't trust the certificate issued by H until we get some more. To answer your question, what is the difference between M and A? We don't trust the keys issued by M, we trust the keys issued by A, half. Okay, so we didn't say actually A, B, C, D who issued the certificates. I can't say why we are doing this in the first row, but we can explain the second row. The first row got found because somebody issued the certificate to A, B, C, D, E, F. Well, we can see F got two certificates. F got at least one certificate from E. So and we trust E fully, and then that would just make it, no, sorry, I'm just the opposite. E is certified by F, not, okay, so the arrow goes to the certifier. So F certified E, alright, and E certified M, N, and O. So, but for D we don't know, okay, let's see. We don't know who certified D. Maybe we met him in person and then we somehow know each other, and so, you know, by this arrow line, we would say that I certified A, B, C, D, E, F. So that for the first row. For the second row, we can clearly see depending on these, we can see why the circles are the way they are. So why the first row is half and this is full? Some other history which is not in this picture. Between C and A. Okay, C is same as M. So let's see. C is same as M. Basically, C, we trust C, but we don't trust the certificates issued by M. And it did issue I, J, and K, but we are not trusting them yet. That's why there is no circle here. A, we trust him half. It issued 2 certificates, G and H. We are not trusting G because G is not fully trusted, but H we are trusting fully because it has 2 half certificates. So everybody issues certificates which are that level of trust. So half level, full level, this is 0 level, full level. So the gray indicates the level of trust on the certificates issued by them. Alright, so that was kind of new. I mean, this we didn't learn before, so level of trust is clearly new stuff. Now the next thing is how to use certificate revocation. So now if everybody is issuing certificate, everybody else, you know, now who do you get the CRL from? So for that, they had a simple scheme where whoever issued the certificate can issue a revocation certificate, and I don't know whether that bugged out or not. Nowadays they just use certificates of expiry dates, so you know, you have to worry about if you revoke it before the expiry date, you have to have the previous method, which is that you have a revocation certificate and you can say this is no longer good. You got the email, but that is not mine anymore. My key was resigned last year, you know, and so on and so forth. So that revocation is not clean. I mean, you know, it's there but not clean. Okay, that's all about PGP. All right, so there are many open PGP products. I don't know whether McAfee makes one or not, but you know, as I said, the PGP code is now owned by McAfee.